Okay, this video is a continuation of the previous video where we worked on examples A, B, and C. In this example number D, we have a polynomial x to the power 2n minus y to the power 2n, and we want to prove that this is divisible by x minus y for all n, for all counting number values of n. If you haven't looked at our videos on polynomials, you might want to do so before you go through this example, because some of the ideas we're going to be using are from that video, obviously this being a polynomial, right? So in step number 1, we are going to let n be equal to 1. Then p, when n is 1, I'm just going to just stick with the n, the x and y. I'm not going to write for brevity. So this is going to be 2 times 1, y to the power 2 times 1. So this is going to be x squared minus y squared. This is a difference of 2 squares, so we can factorize like this. So this is a polynomial times x minus y. So that means this is divisible by x minus y, which is divisible by x minus y. By the way, so in the context of polynomials, a polynomial is divisible by whatever factor, x minus y in this case, if the polynomial can be written as that factor times another polynomial. So this would be our quotient, if you like. So this polynomial divided by x minus y is going to give us x plus y. Okay, so then in step number 2, we are going to assume that the polynomial, which is this one here, is divisible by x minus y when that n takes the value of k. So we're going to assume that p of x, y of k, x to the power 2k minus y to the power 2k is divisible by x minus y, where n, or rather k, where k is an integer. Let's just say where k is a natural number. Okay. Now, of course, assuming that this is divisible by x minus y implies that x to the power 2k minus y to the power 2k must be equal to x minus y times a polynomial this time. So let's call that polynomial, we've already used p, so let's call it q. Actually, q works very well because it also stands for quotient. So, but our quotient, we need it to be a polynomial where Q is a polynomial. Okay, so that is the implication of this assumption there. Then in step number 3, we need to test whether P of xy of k plus 1. So where there's k, we're going to plug in k plus 1. So there's k here, there's k there. So this is going to be x to the power 2 times k plus 1 minus y to the power 2 into brackets k plus 1. Let's simplify now before we finish the sentence. So this is x to the power 2k plus 2 minus y to the power 2k plus 2. So I want to test whether this is going to be divisible by x minus y, provided that step 2 is true. From step 2, here we can make x to the power 2k the subject of the formula. So we so let's say from step 2, we have x to the power 2k is going to be equal to x minus y times q plus y to the power 2k there. So we've just taken this term to the right hand side. Then we must look to substitute this somewhere there. So in a process a bit similar to what we did in our previous example, I'm going to so let me just write this out first. 2k plus 2 y to the power 2k plus 2. Now I'm going to write this as x to the power 2k times x to the power 2 minus y to the power 2k times y to the power 2. Then we are going to take this here, take this and substitute it there. Okay, so this is going to give us, let me just write the x squared out first here. So this x squared is that one there. So then x minus y times q, remember q is a polynomial, y to the power 2k, then minus y to the power 2k times y squared. So that's just that term there. And then remove brackets, x squared x minus y times q plus x squared times y to the power 2k minus y to the power 2k times y squared. And then all of a sudden we have a common factor here, which we are going to factorize. So when we do that, x minus 1q here, we're going to have y to the power 2k into brackets x squared minus y squared. But then this is now factorable, so we're going to factorize that. So we're going to have x squared x minus y times q. It's going to be x minus y, x plus y. And then x minus y is now common factor, so x minus y brackets x squared times q plus y to the power 2k x plus y. Now q is a polynomial, x squared is a polynomial, so x squared q is also a polynomial. X plus y is a polynomial, there's a polynomial, so there's a polynomial plus a polynomial is a so this whole thing here is a polynomial here. So this is a polynomial. So p of k plus 1 is equal to x minus y times a polynomial. So p of x plus k plus 1 is divisible, which is divisible by x minus y. So that is telling us that p of x, y, n is divisible by x minus y for all values of n that are counting numbers. So yeah, that brings us to the end of part D. We're now going to give you 3 exercises to try and prove by mathematical induction on your own. If you want to pause the video, work them out, and then you can compare your answers afterwards by pressing play. So if you want to pause, let's just put the examples up for you. Alright, so please have a go at these 3 propositions. So just press play, pause, work through them, and then you can compare your answers with ours upon playing the video again. So if you want to just press pause and work through them now. Alright, so for E, we have got P of n equals n into n squared plus 5. This is divisible by 6. That's what we are supposed to prove. So if we try this for n equals to 2, P of 2 is equals to 18. Now, of course, this is divisible by 6, so this is, the proposition is true for n equals 2. Then we assume that for some value of n equals k, where k is a natural number, k into k squared plus 5 is divisible by 6. What this means, if you remove brackets here, is that k squared plus 5k is equals to 6z, where z is an integer. Then in step number 3, we want to prove whether for the next bigger integer, p of k plus 1, which is going to be obtained by replacing k by k plus 1 here, k here, k plus 1 there. So I want to prove whether that is divisible by 6 as well. If we expand this, we get k cubed plus 3k squared plus 8k plus 6. Now from step 2, from this step here, k cubed is equals to 6k minus 5k. If we take this and plug it in here, then we're going to get that p of k plus 1 is 6z plus 3k squared plus 3k plus 6. If we factor this out, 6, then z is an integer, 6 is an integer. The question is about this one. This one is half of an integer plus times the next integer. Is this always going to be an integer? And the question is yes, because this integer is odd, this one will be even. This one is even, this will be odd. So the product of one integer times the next integer is always going to be even. So this is even. So half of an even number is always going to be an integer. For instance, 2 times 3 is 6. 3 times 4 is 12. 5 times 6 is 30. So an integer times the next bigger integer is always going to give us a product which will be even. So this term here, even though it might not look read immediately like an integer, there's an integer. So there's an integer plus an integer plus an integer. So there's 6 times an integer. So this is divisible by 6. And therefore the proposition is true for all n that are natural numbers. Okay, in F, want to prove that a to the power n minus 3 to the power n is always divisible by 5. For n equals 1, this gives us 8 minus 3, which is 5, which is divisible by 5. So for n equals 1, the proposition is true. Then we assume that the proposition is true for n equals k. So assume this is divisible by 5. So this implies that a to the power k minus 3 to the power k is equal to 5z, where z is an integer. So in step 3, we want to prove whether p of k plus 1, so every k here will be replaced by k plus 1, whether this is divisible by 5. From step number 2, if we make 8 to the power k subject there, we have got 5z plus 3 to the power k. Then we can take this and plug it in here. So first we write this as a to the power k times 8. This 3 to the power k times 3. Then if we take this and substitute it here and remove brackets, we're going to have 4z plus 8 times 3 to the power k minus 3 to the power k times 3. Now 3 to the power k is a common factor there, so if we factorize that, that's going to give us 5. Now there's a common factor of 5 here and here, so this is 5 times 8z plus 3 to the power k. This is an integer, that's an integer, so this thing is divisible by 5. So that tells us that the proposition is true for all natural numbers. In G, we have got 3 to the power n plus 2 plus 4 to the power 2n plus 1. We are told that this is divisible by 13. So if we try n equals 1, this gives us 3 to the power 3 plus 4 to the power 3, that is equals to 91. Well, we can just check here that 91 is divisible by 13. So the proposition is true for n equals 1. Then we assume that when n is some integer k, natural number, this is divisible by 13. So that means 3 to the power k plus 2 plus 4 to the power k 2k plus 1 is 13 times another integer or natural number. Then want to prove that whether p of k plus 1 is divisible by 13. So here k plus 2 became k plus 3. 2k plus 1 becomes 2k plus 3. From step number 2, which is this one here, 3k plus 2 is 13z minus 4 to the power 2k plus 1. So if we take this thing here and plug it here, then and multiply out, we're going to get 39z minus 3 times 4 to the power 2k plus 1 is 4 to the power 2k times 4 to the power 1. So, and 4 to the power 2k is now common. We factor that out. It's going to give us 52. Then 13 is a factor of this and this. 13 goes 3 times here and 13 goes here 4 times. Now there's an integer, that's an integer. So this now is 13 times an integer. So this is divisible by 13 and hence the proposition is true for all values of for all natural numbers. Alright, so that just completes our number 1. In the next video we're going to start number 2.